So when you're comparing two proportions, now we've talked about one population proportion. So this is just kind of stepping that up. So that's good news, because it's relying on prior knowledge to some extent, but it's also not overly challenging. So that's good news. The test statistic formula is going to be kind of interesting to look at, but we'll cross that bridge in a minute. So we're talking about two independent simple random samples. The conditions for a binomial distribution are satisfied, and all these other conditions. Oh, more and more conditions. NP greater than or equal to 5, NQ greater than or equal to 5, mu is equal to NP, sigma is equal to NPQ, square root. All right, but that's all stuff that the calculator is going to handle for you. So it's really not that big of a deal. What we need to do is really focus on framing our solution in terms of the null and alternative hypotheses. That's really where you kind of earn your keep with something like this. All right. So that it's going to come down to interpreting the question correctly. First off, in order to determine that it is a population proportion question, and then on top of that, what information is relevant and what information is extraneous. Right? So that's where we're going. The null and alternative hypotheses kind of look weird, but most people are sort of, or most people have in the past, sort of gravitated towards these variations because they seem to kind of make more sense. But for example, P1 minus P2 is equal to 0. That's actually the same as P1 equals P2. If you really think about it algebraically, if I say P1 is equal to P2, and then subtract the P2 from both sides, it would cancel on the right, and you would get P1 minus P2 on the left-hand side with a 0 on the right. So that's where this is coming from. So it's actually basically the same thing, right? But that P1 minus P2 equals 0 is going to help us actually simplify our test statistic formula significantly, which is good. All right. So let's dive into the situation, if you will. So we'll just jump right to an example because you can see the structure is essentially the same. And that's the kind of familiarity I was talking about before. It'll make life a little bit easier in that you can start relying on certain things being true. Like, for example, the significance value, the alpha, that's going to be the same value or set of values from hypothesis test to hypothesis test. What you do with the p-value as opposed to the alpha, that's the same idea also. This complete graphing calculator approach, that's old school. That's all from a TI graphing calculator. So this one should actually be the normal distribution. It's a normal dist. Right. So it's an old problem. I mean, you can pretty much tell when I type these notes up because there's a lot of references to 2003. So that is what it is, if it ain't broke. And also, I mean, I don't know how many people are football fans out there, but I still have yet to see a better pure quarterback than Peyton Manning. I mean, I know some people are Tom Brady fans, but in terms of just throwing the football, I've never seen anyone better than Peyton Manning. So a lot of my stuff, especially when it deals with sports, is Manning centric. All right. So anyway. A study was conducted to determine if the ratio of passing touchdowns to passes attempted by Peyton Manning has increased. You see, like it's even like in that moment in terms of the phrasing, has increased instead of had increased between the years of 2003 and 2004. In 2003, Manning attempted 566 passes. 29 of which were touchdowns. All right. You don't have to have any experience with football, American football, in order to understand, hopefully, that the 566 represents some number of trials, 29 of which were successes. Right. So if you're not familiar with football, you can kind of equate a touchdown. I mean, it's not quite the same, but it's on the same level of importance as a goal in hockey or soccer, or a home run, or any kind of run in baseball. But it's a scoring play, right? In 2004, Manning attempted 497 passes, 49 of which were touchdowns, right? Using a 0.05 significance level. And so you can just jot that in immediately, 0.05. Statistic claim that the population proportion of touchdown passes has significantly increased between the years of 2003 and 2004. So the way we would look at this in terms of the information that's being provided, we have two categories. We have 2003, we have 2004. In 2003, we had 566 trials, 29 of which were successes. In 2004, we had 497 trials, 49 of which were successes. So we kind of run into a problem in terms of notation here, because we have two n's and two x's. We would want to distinguish one from the other. So what I would do is I'd use subscripts. Since 2003 is my first set of information, I'd sub those with ones. 2004 is my second set of information, so I'd sub those with twos. All right, just to distinguish them from one another. All right. So we need a distribution associated with a 5% significance level. We also need a test statistic. There's a lot of stuff that's going on here that we need. So I'll start drawing my diagram anyway. Poorly. All right, the best I can do. I'm going to open a fresh Desmos, because it's not a t distribution. All right, the test statistic is a pretty crazy looking formula. It's z is equal to p hat 1 minus p hat 2 minus p1 minus p2 over the square root, if it locks in, of p hat 1 q hat 1 over n1 plus p hat 2 q hat 2 over n2. There's other variations of the formula, but this one doesn't make any assumptions about the population parameter. All right. So the one thing that probably pops out at you is those p hats with the ones on, subscript of 1 and 2. Look at that and say, well, what on earth? What did I get myself into? Yeah. Did the withdrawal deadline pass already? Stuff like that. It's really not that bad. The p hat, oh, I always do that, is x divided by n. The subscripts are just referring to each individual data set. So p hat 1 is x sub 1 over n sub 1, which would be 29 over 566. You can go decimal form if you want. I don't really recommend that. The reason being that you kind of run into rounding considerations when you do that. If you go into decimal form, if you leave it as a fraction, Desmos can handle fractions. Just leave it as a fraction. You don't have to worry about screwing it up based solely on rounding. So x2 over n2 is going to be 49 over 497. I'm just going to move this down a little bit because it's getting a little cluttered. All right. So then you might look at it and say, okay, well, that's all well and good. Now, what the hell is this Q hat business? Right? Because we got the P hat 1 now, we got the P hat 2. We don't have anything related to Qs. We do have the N1s and N2s. So we got a good chunk of the formula, but we don't have the enough of it to get the job done. Right? Q hat is 1 minus P hat. So Q hat 1 is 1 minus P hat 1. Q hat 2 is 1 minus P hat 2. Right? So if you know P hat, you actually know Q hat. All right? It's just a matter of subtracting that P value from 1. And you just got to be careful because I say P value a lot. These P's, the population proportions, are different from the P value, which talks about whether or not you're rejecting the null hypothesis. So as if this stuff wasn't as confusing as all hell to begin with, we just made it a little bit more mind-bending. But we'll get to computing the test statistic because, again, we want Desmos to do that work for us. It's not going to look pretty in there, but it's still better than having to do it by hand. All right. Now, the question that's being asked here, test the claim. I'll zoom back in on that in a minute, but test the claim that the population proportion of touchdown passes has significantly increased between the years of 2003 and 2004, right? So when you think about increasing, you should be thinking about the previous value being smaller than the subsequent value. So if I tell you that my height increased over the course of a year, so from, let's say, the year 2020 to 2021, that means in 2020, I was shorter than I am in 2021, right? So what this is saying is that the population proportion in 2003, that's my first group, my population proportion for the first group is actually less than the population proportion for my second group. All right, so I have my two groups. 2003 is subbed with subscripts of 1. 2004 is subbed with subscripts of 2. So that's how I note it. Instead of having hats over the P, that means the P hat refers to a sample proportion. Without the hat, it's talking about a population proportion. That's what we care about. All right, we're talking, it says it right here, population proportion. That's P. All right. Now, the null hypothesis, just like in the t-test and the one population proportion test, the null hypothesis is going to have the same ingredients, just with an equal sign. All right. So these are our two choices. It's either the case that there was an increase or we don't know. There's no reason to suspect there's any difference between 2003 and 2004. That's what the null is saying. All right, but the alternative is saying no, there's an increase. All right, so it's just a matter of how substantial that increase is. But that's not what a hypothesis test will give us anyway. It'll just tell us whether there's a significant increase. It just won't tell us what the amount of increase is. Further investigation is required for that. The calculator test is the normal distribution. What I mentioned before. Because it is an alternative hypothesis that involves a left-facing inequality. Right? So less than symbol talks about a left-tailed test. Right? So left-tailed. So that means all of my alpha goes on the left side of the graph, 0 in the middle. I'm looking for a critical Z value now, right? Not a T value, but a Z value. So anytime you have a population proportion, we're talking about Z rather than T, all right? T's go with population mean. So that's the mu. That's the Greek letter mu that we did in the last example. But anytime you have a P in your null or alternative hypotheses, it's a z-test. All right. So the way we grab this value is by using the inverse CDF function for the normal distribution. So just like we did with normal distributions and central limit theorem, we're going to grab the probability, or we already have the probability. We're going to grab the Z statistic, or the Z critical value associated with that area of 0.05 to the left. All right. So the way we crank that out, again, function, distribution, inverse CDF, function, normal distribution, 0, 1, close it up, comma, 0.05. And so we get our critical value of negative, if we're going with 3 significant, negative 1.645. All right, so that gives us our cutoff, our critical value. All right, the shaded area is the rejection region. If our test statistic falls in that shaded region, and we're about to compute the test statistic, if it falls in that shaded region, then we reject the null hypothesis. If it doesn't, then we don't. All right, so we got to crunch some numbers. The way we crunch the numbers, I like to put it in as Z equals. And then this whole monstrosity of a fraction, I mean, trying to get sliders to work for something like this it's doable, but it doesn't look pretty. Because just like there's no X bar, there's no P hat. So it's subscripts galore, it's hideous. All right. So like I actually tried making it just to try to make life a little easier. And it was kind of a non-starter, because I needed subscripts for the ones, and then I needed some way to represent the hat. It was too messy. It was more confusing than helpful. All right. So P hat 1 minus P hat 2. So fraction inside of a fraction, 29 over 566 minus P hat 2. So fraction 49 over 497. Minus parentheses P1 minus P2. Now that's an interesting one, because the P1 minus P2, that's an assumption. So that's an assumed value. All right. So that comes from the null hypothesis. All right. And right up here in this neighborhood, we talked about P1 equals P2 being the same idea as P1 minus P2 being equal to 0. All right, so that gave us this relationship. So long story short, we can actually replace this whole thing with the number 0. So you can actually disregard it, because it's always going to 0 out. So you could put in a -0, or you could just disregard the minus part. So that's kind of like, I mean, not much of a shortcut, but it's something, you know. So on the bottom, you have a radical, and you have a sum of 2 fractions. So P hat 1, again, is the fraction of 29 over 566. Now we have to multiply that by 1 minus, so the Q value, which is 1 minus the P hat value. All right, so Q hat 1 is 1 minus P hat 1, which is 1 minus $29 over 566. Like I said, this is going to be a monster, but it's still a lot better than doing it by hand. Right? The N1 value is 566. Then we got to add to this, still within the radical, everything associated with p hat 2. So another fraction within a fraction, 49 over 497 times 1 minus that. And the only reason I'm writing 1 minus that is because I don't want to actually figure out what 1 minus the 49 over 497 is. I mean, it's actually not terribly, or 48 over 497. But it's still something that I don't want to have to follow. So 1 minus 49 over 497. Close it up, 497. And what you get from this, and I'll just move it over a little bit so you can see the whole shebang in its full glory, is this beautiful looking expression. Right? So that's pretty nasty, but it's also, like I said before, something that Desmos is doing for you so that you don't have to do it yourself. So, I mean, that's the trade-off. I mean, you take the time to type it in so that you don't have to go nuts trying to do it by hand. Right? So we get a test statistic of negative 2.911. All right. And just like the last hypothesis test, it's a question of where this falls in relation to your critical value. All right. So I would look at my graph, negative 2.911. I don't know where that is, but if I know negative infinity is going this way, it's going to have to be somewhere to the left of the critical value. So maybe somewhere like here. I don't know. It doesn't matter as long as we know that it's in the shaded area. Right. So we're looking at a case where we would reject the null hypothesis because it's falling into the shaded region, which would mean that the alternative is the one that's true. All right. But we also need the p-value. Right. So what the p-value is going to be is actually, it's computationally, it's not bad. It's just an extra step that nobody really wants to do at this point. I mean, there's also the case where it's doubtful that you wanted to do the first 20 steps of this problem to begin with, but yeah, it's just it's one of those like out of the frying pan into the fire kind of things. Yeah, it's really it's not that bad, but it feels like it is. Right? So the p-value is going to be the probability that z is less than negative 2.911. All right. So that's why we did all that normal distribution central limit theorem stuff. Right. The big question that I would imagine is on somebody's mind would have to be, well, how do you know where does this less than business come from? All right. So that comes from the alternative hypothesis. Whatever the alternative hypothesis is dictates what the sign is going to be in the p-value computation. All right. So what we do is we use normal distribution with a 0, 1. All right, that'll create the normal distribution, as you probably would have expected. And what we do is we max out the graph at whatever we came up with for z. So for cumulative probability, I don't want the whole thing. I don't want it to go from negative infinity to infinity. I want it to go from negative infinity to whatever I came up with for z. All right. So what I'll do is just do a quick screenshot of this and pop it into the notes so you have it. I don't need the screenshot. I just wanted in there. All right. And that has to do with, if we're talking about going from negative infinity to z, that's the same as saying z is less than whatever that number is. So that number that we established, I'll use the yellow, is negative 2.911. That's the z value that we're going up to. Right now, if you look at the picture, it doesn't look like it really did anything, but it actually did. We got the p-value of 0.00180. If you look closely at the graph, I could change my window again. I don't like the default here, but it is what it is. So you look at this and you say, oh, I don't see anything. But you got to understand it's somewhere around negative 2.911, which is going to be over in this neighborhood. If I bring it in closely, you can see that there's a little teensy tiny little bit of shading there. That little teensy tiny little bit of shading is associated with the p-value. All right, so that p-value of 0.00180, which I can tuck in here. Oh, looks hideous. That little 0.00180 is definitely less than the alpha value. So again, if the p-value is less than the alpha value, we reject the null hypothesis. So whether it's from the diagram or the p-value, we still get the same result. P-value is less than alpha, reject the null hypothesis. So then it's just a matter of writing our conclusion. All right. So easier said than done, of course, but if you got through all the computations, then odds are this part, I don't want to say it's a piece of cake, but in comparison, it sure is. Right. So there is, if we're talking about the first sentence being a case where we're rejecting the null hypothesis or not, we will, I'll get to that question in a second. If we're talking about a case where or the first sentence where we're talking about rejecting or not rejecting the null hypothesis, then sufficient or insufficient evidence is going to be specific to what we determine over here, right? So here I'm saying I am rejecting the null hypothesis. We got a big old X there. So that means that there must be sufficient evidence to reject the null hypothesis. Now that null hypothesis is related to population proportion of touchdown passes, right? So, and whether or not they're equal. So there's sufficient evidence to reject the claim that the population proportions of touchdown passes, TD passes, are equal at the 0.05 significance level. Therefore, the claim that we're either talking about the alternative hypothesis or the question that's being asked or some mixture of the two. The alternative hypothesis says simply P1 is less than P2, but that came from the question that says population proportion of touchdown passes has significantly increased, right? So therefore, the claim that the population proportion of touchdown passes increased. Well, that's going to be true. It's got a big old check mark next to it. So that's got to be the true sentence. Right. So the question was, how do we know which calculator to use on a test? And that's a good question. It's related to the type of hypothesis test that you're working on. So in this case, we're talking about a population proportion. So that means that we're dealing with a z-test, right? Anytime you see the letter P in your null or alternative hypotheses, you're dealing with a z-test of some kind, right? So this is going to be a z-test, which means normal distribution. All right, so that's normal distribution. Now, if you look at, just go back to the other set of notes here, if you see a mu in your null hypothesis or alternative hypothesis in any capacity, the mu is talking about the t-test. Right, so any instance in which you see a mu means that you're working off of a t-test. All right, so let me stop that recording.